Hi, I'm Andrea, and this is AP Physics C Mechanics FRQs. Today we're going to be talking about 2019 Set 2 Question 3. So the question says, the rotational inertia of a rolling object may be written in terms of its mass m and radius r, as I equals bmr squared, where b is a numerical value based on the distribution of mass within the rolling object. Students wish to conduct an experiment to determine the value of b for a particularly hollowed sphere. The students use the loop track of radius capital R is much greater than small r, as shown in the figure above. The sphere is released from rest, a height h, above the floor, and rolls around the loop. So the overall situation is this partially hollow sphere starts at rest on top of the track, rolls down, and rolls around this loop. And we're given this equation for inertia. So when I think of rolling, I think of, okay, we're going to use rotational equations. Since the sphere is released from rest at a height of h, we might use conservation of energy equation. And since we're going around a loop, I like to think of centripetal force. Part A. Derive an expression for the minimum speed of the sphere's center of mass that will allow the sphere to just pass point A without losing contact with the track. Express your answers in terms of these variables and fundamental constants as appropriate. So they want to find the linear speed at point A. When I think of linear speed, I either think of using conservation of energy, using basic rotational conversions, or in this case, centripetal force. An important thing to note, this question also uses the key term derive. So we have to use an equation from the equation sheet to find our answer. For this question, I like to use centripetal force because one, the sphere is in the loop. Two, centripetal force directly relates to the linear speed of the sphere at the point. So we start with our initial equation. Centripetal force equals mass times velocity squared over r. This mass is the sphere's mass, this velocity is the velocity of the sphere at point A, and this r is the radius of the loop. And we know that centripetal force is the net force of the sphere at point A. So it equals F net. So looking deeper into F net, we know that the sphere at point A will experience gravitational force and normal force, since it's touching the track. So we know that the gravitational force is just mg, but an important thing to note is that the normal force, since the sphere is just barely touching the track, is actually 0. But we're just going to choose the parts with variables in it. So mv squared over r is equal to mg. The m's cancel out, you can move the r over to get v squared equals rg. So you take the square root of both sides to get that v equals square root rg. And that is your answer for part A. Part B. Suppose the sphere is released from rest at some point P, rolls down without slipping. Derive an equation for the minimum release height h that will allow the sphere to pass point A without losing contact with the track. Express your answers in terms of these variables and fundamental constants as appropriate. The question uses the key term derive, which means we have to use an equation from the equation sheet or an equation that we've derived in the answer before. So if we're finding the minimum release height h, which is this height here, first thing I think of is conservation of energy. So you need an initial and final moment. So for initial moment, I'm just going to choose when the sphere is at rest at height h, and for the final moment, I'm going to use the sphere at point A. Since the value of small r is negligible compared to the value of big R, we can just say that the height is 2r. So whenever I use conservation of energy, I always like to explicitly write it out so that the grader has an easier time of understanding which concept I'm actually using. So initial energy is equal to final energy. Since the sphere is rolling, we have to keep rotational kinetic energy in mind as well. So we have initial potential energy plus kinetic initial equals potential final plus kinetic final. So originally the sphere is at rest at a height of h, so the potential energy is mgh plus, since the sphere isn't rolling and it's at rest, since the sphere is at rest, its linear kinetic energy is 0 and its rotational kinetic energy is 0 because it's not rotating either. So its total initial kinetic energy is 0. Now looking at the final potential energy, we know that the sphere is at a height of 2r. So the final potential energy is mg2r. Now we're going to break the kinetic energy down into linear kinetic energy and rotational kinetic energy. So linear kinetic energy is just 1/2 mv squared, and rotational kinetic energy is 1/2 I omega squared. So we can't really simplify the left side, so let's look at the right side. So this value of v is the value of the velocity at point A, which we've actually found in part. So we can use that value and plug it in for v. For I, we can just use this equation here, and for omega, which is the angular velocity at point A, we can use the relationship of linear velocity and angular velocity, which is v equals r times omega, which means that omega equals v over r. And hey, we know this linear velocity of v is the same linear velocity v at point A, and it's the same as this value of v. So we plug those values in for these three more complicated variables to get that mgh is equal to 2 mgr plus 1/2 mgr because v squared is root gr squared plus 1/2 bmr squared times omega squared. Always remember the square. Alright, so we're going to simplify the right side even more to get that 5/2 mgr by combining these two terms here, plus we can actually cancel out this r squared with this r square, 1/2 bmv squared, and we can substitute root gr for this v again to get that the right side equals to 5/2 mgr plus 1/2 bmgr. Left side is mgh, so we can cancel out mg on both the right side and left side to get that h equals 5/2 r plus 1/2 br. And you can just leave it like this in a test, it's totally fine. The grader shouldn't mark you wrong, but if you want to simplify this to the cleanest way possible, you should take the r out, take 1/2 out, get 1/2 r times, this would be 5 plus this would be b, and that is your answer for part B. So we're given new information that the students perform an experiment by determining the minimum release height h for various other objects of radius r and known values of b. They collect the following data of these different objects with different b's and different h's. So part C, on the grid below, plot the release height h as a function of b. Clearly scale and label all axes including the units if possible. Draw a straight line that best represents the data. So since it's release height h as a function of b, you won't know on the y-axis it's going to be h, x-axis it's going to be b. So it says to include all units, and looking on the chart on the left, we can find out that b has no units and h has unit of meters. So make sure to label that. An important thing to note when graphing graphs is that the axis doesn't have to start from 0. It can, but it's not necessary for plotting the graph. A general rule of thumb in my mind is that you have to use at least 3/4 of the grid, but AP just requires you to use at least half. But no matter what, the best case scenario is if you use the whole graph. So that's what we're going to do now. So look at the values of b. We're going from 0.4 to 1, and we have 4 major sections. So I'll just label it from 0 to 1. Since all these values have at least 2 significant digits, we should make sure that ours also has at least 2 significant digits. For 0, it doesn't matter because 0 is just 0. If you want to write 0.00, that's up to you. So we're going to start from 1.00 for h, and we're going to max it at 1.20. Make sure the values on your axes make sense. Alright, so now we have to actually plot the points. So I sped up me plotting the points, but on the AP test, make sure you take your time to plot the points correctly. And one confusing thing over here is that b doesn't go strictly increasing. It goes from 0.4 up to 0.67 and then back down to 0.5. So make sure that you're paying attention to the values as you plot them along. So just draw a line of best fit, and always make sure to use a ruler during this process. That seems like a good line, and oops, I plotted that point wrong. It's 0.67, 1.13. So 1.3 is actually here, 0.67 is a bit off, so this point is actually here. Make sure to fix your points before drawing the line of best fit, otherwise your line going to be a bit wonky. Alright, that's your answer for part C. Part D. The students repeat the experiment with the partially hollowed sphere and determine the minimum release height to be 1.16 meters using the straight line from part C. Determine the value of B for the partially hollowed sphere. So the question gives us that for this particularly hollowed sphere, the value of H equals 1.16 meters. Since we need to use the line from part C, we need to find the line of best fit that we've drawn in part C. So looking back, we see that we need the slope of the line and we need the vertical intercept of the line. So there's 2 ways to approach this. One way is to use a calculator and use linear regression with the actual specific points to find the best fit line, or you can derive the line equation based on the graph, plug h in to find b. Whichever one seems more convenient, although the linear regression one does give you a much more clear answer and a much easier time for the grader. But for this question specifically, I see that the line intersects 0, 1 and 1.2, so it's easy for me to find the slope and it's easy for me to find the actual equation of the line, because one of these values is actually the vertical intercept, 0, 1. So going back to our workspace, we know that the line has the points 0, 1 and 1.2. So we need to find the exact equation of the linear line. So the general equation of the line is y, which we're going to use h equals x, we're going to use b plus c. So we need to find the slope and vertical intercept. So we actually have the vertical intercept here, so we know that c equals 1, so we need to find m so that we can plug it in, and then we can plug in h to find the value b. So m is the slope, so slope equals m, which equals y2 minus y1 over x2 minus x1. And since we have these 2 points, this is the first point, this is the second point, we can plug them in to get that 1.2 minus 1 over 1.0 minus 0 is equal to 0.2 over 1, which is just 0.2. So we plug all these into the equation, we get that h equals 0.2 b plus 1. You plug h in and solve for b. So you get 0.16 equals 0.2 b. You get the b equals 0.8. And there's no units for b. And this is your answer for part D. Part E, calculate big R, the radius of the loop. So this seems completely unrelated to h and b and stuff. And I frankly don't really have an idea of how to solve this. So I'm going to look at my previous part's answers to find if there's an equation I can use or if there's any way that I can maybe follow to find it. Things to keep in mind is I'm looking for R, and from the experiment in part D and C, I have values of H, I have values of B, so we're going to need to use these 2 values to find R. So I'm looking for an equation with these 2 values in R. Looking back into the question, you can see that in part B, we actually have an equation with all these 3 variables in them. We got that H equals 1/2 R5 plus B. So since we have this relation from part B, we have value of H from part D of 1.16 meters, we have B 0.8, and we can plug this all in to find R. So 1.16 equals 0.5 R5 0.8, and use your calculator to get that R equals 0.4. And we need units. Since R is a length, we can use meters, since H is in meters too. And that's your answer for part E. Alright, part F. In part B, the radius r of the rolling sphere was assumed to be much smaller than the radius r of the loop. If radius r of the rolling sphere was not negligible, would the value of the minimum release height h be greater, less than, or the same? And justify your answer. Part F. In part B, the radius r of the rolling sphere was assumed to be much smaller than the radius r of the loop. If the radius r of the rolling sphere was not negligible, would the value of the minimum release height h be greater, less, or the same? So it wants us to compare this new height h with the old height calculated in part B. So let's imagine a sphere with a radius that's much larger than r in the diagram. So in part B, we're not only looking at the minimum height of release, we're also looking at the sphere at point A. So let's put this big sphere at point A. We can label its center of mass, which is far away from the point of contact on the track. So if the sphere were to go through the loop, you'd see that its center of mass actually travels not along the track, but like this smaller circle within the track. So if you recall in part B, we use this big radius r to calculate the minimum release height, but we can't apply this big R because the center of mass of the sphere doesn't reach the top of the loop. If we take R to be the radius of the loop that the center of mass of the sphere travels, in this new situation, R decreases. Since R decreases, the final height of the sphere also decreases. And since this final height decreases, the final potential energy decreases, which means the final total energy decreases, which means that the initial energy, in order to follow the conservation of energy, would also decrease. So this initial mgh, with the h as the initial minimum release height, would have to decrease in this new situation. So going from the calculated height to the new height, the value would have to decrease, so the calculated height is greater than the new height, or in other words, the new height is less than the calculated height. And it's the first part of your answer for part F. So the next part is justification. So you just lead the grader through your process of getting to this answer. So my justification would be that if the sphere's radius is not negligible, then the radius of the loop the sphere's center of mass travels is less than r, and the maximum height the sphere travels through the loop decreases. This leads to the minimum release height of the sphere to also decrease. There are better justifications for this question. There are also different justifications for this question. As long as you can logically lead your grader through your process and get to the correct answer, then it's okay. AP Physics C doesn't like you spending too much time on justifications, so 1 or 2 sentences should be enough. You don't have to write a whole paragraph to justify your answer, because that takes too long and you don't have that much time in AP tests. So this is my answer for part F. So if you're still confused about how in the world did I get that, oh, this question needs conservation of energy, or this question needs rotational conversions, there's a link in the description that will lead you to a Google Doc of my categorization of every year's overall question and every year's question's parts, concepts. So if you go to a specific concept, it'll lead you to another Google Doc where I explain how you can identify a concept through a question. I hope that I've helped clarify this question for you, and I'll see you in the next explanation video. Bye!